Hello everyone. Welcome to the first lesson of the first unit of Ontario's Curriculum Advanced Functions. Today we're going to be learning about power and polynomial functions. So just to start off, what is a power function? Well, a power function is the most basic function in math. It is simply equal to a to the x to the power of n. And so in there you might be like, what is the a, what is the x, what is the n? Well, that's pretty simple. The a is just the coefficient. The x is just the variable. And the n is the exponent. And from there, we can try to map out a pretty basic function. So let's just start off with what will be known as y is equal to x to the 3. So that'll look something like this. That's just an approximation, of course, but this is just to get you to understand the general functionality. A lot of them will look somewhat like this, but there's actually 4 different general shapes that they can take. So those include a positive parabola, a negative parabola, a positive saddle like this one, and a negative saddle like that one. So if any of your functions look something like these 4, it is probably a power function. You might be wondering, what does that have to do with polynomial functions? Well, in fact, a polynomial function is just multiple power functions added to each other, like this. But of course, it's never that simple. So for a polynomial function, our general form will be a to the n, and then x to the power of the n, plus a n minus 1 x n minus 1. And then we can do it again if we want. So that's a n minus 2 x n minus 2. And then it just goes on forever until we get to a1 x1 and then a0 x0. But of course, x0 ends up just being 1. So it's just a0, which is in fact our constant value. So looking beyond that, we can see each of these is just a power function in itself. Just like that. And a couple examples could be, for example, f to the x equals 3x4 plus, let's say, 8x3 plus 2x2. And let's just add in a 0, x to the 1 plus 3x0. So this will just give us the function of f of x is equal to 3x4 plus 8x3 plus 2x2 plus, this is just 0, that's just 1, so we just put a 3. So that's just an example of what a polynomial function can be. And so let's just move on to what end behavior is. You might be wondering, what is end behavior? End behavior is just asking the question, what is y when x extends to plus or minus infinity? So there's 2 possible scenarios here. So y when x extends to positive infinity, and y is what when x extends to negative infinity. So let's take, for example, our past function, which was just x to the 3. We'll just put it right here. So that was something like this. So that's x to the 3. So if we look here, we can see while this is x and we go towards infinity, our y will just continuously increase forever. So we know that y will tend to infinity, and that's positive infinity. But if we look on the other side, this is still x, and if we go down here, we see when x goes to negative infinity, y will also go to negative infinity. And so we can summarize that just by saying when x tends to positive infinity, y will tend to positive infinity. When x tends to negative infinity, y will tend to negative infinity. It's that simple. And so let's look at what the quadrants are. This is another way of expressing what we've already tried to express above with end behavior. In the world of quadrants, there is 4 possible. There's 1, 2, 3, 4. They are always in this order and always expressed in Roman numerals. So we start here and we go counterclockwise like that. And so when we want to express x tends to positive infinity and y extends to positive infinity, and when x tends to negative infinity, y extends to negative infinity, we can just summarize that by saying f of x follows the behavior of the third quadrant to the first quadrant. Because we can see when x is positive and y is positive, we are up here in quadrant 1. But when x is negative and y is negative, we are down here in quadrant 3. And the function goes all the way up here and then all the way up into quadrant 1. And so that's why we can say that it goes from quadrant 3 to quadrant 1. And so let's try to come up with some general rules for what we've just established. So here I've come up with the four basic shapes that we listed off earlier. And for each one, we're going to identify the behavior in the quadrants. So, for example, here, when the exponent is even, because 2 is even, and the coefficient is positive because it's like there's a 1 there, we can see it goes from quadrant 2 to quadrant 1. So we'll just write that there to quadrant 1. But we can see if the exponent is still even, but the coefficient is negative, we can see we just go from the third quadrant to the fourth quadrant, just like that. And then finally, we can see if the exponent is odd. Here it is positive for the coefficient, so we go from quadrant 3 to quadrant 1 up there, so we'll just write 3, 2, 1. And finally, if the exponent is odd and the coefficient is negative, we go from 2 to 4. So we'll just write that there, 2 to 4. And obviously these are just the generalizations, but in fact this works for every function that you can identify the exponent and the coefficient. These rules will apply. This is not something that you necessarily need to memorize. It's more something you can do intuitively on an exam or a test. You can just write it down on a little piece of paper because it's pretty straightforward once you understand the logic behind it.